Library of functions. For each of the functions in our library, create a table of values to graph the function. The first one we have is the identity function. We're just going to choose arbitrary numbers for x. X is our independent variable, so it can be anything we want it to be. With the library of functions, we're going to look at several different main functions and see what their sketch looks like. The first is the identity function, f of x equals x. X is our independent variable, so we can choose some starting values. We'll keep them close to the origin. And now just find their corresponding y values. If you plug in -2, we get -2. If you plug in -1, we get -1, and so on. And then we can graph this. Plot your 5 points, and then play connect the dots. And this is our identity function. Next, we have the square function. Again, we'll choose some starting values for x. Just keep it close to the origin. And let's find the corresponding y values. We're just squaring each of these numbers. -2 squared is 4. -1 squared is 1. 0 squared is 0. And so on. Plot those points. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. Play connect the dots. This time we'll do a smooth curve. And we have a quadratic. Next, we have x cubed. So just cube each of your x values. -2 cubed is 8. -8, excuse me. -1 cubed is -1. Then we get 0, 1, and 8. Plot those points. -2, -8 is a little off the grid. So is 2, 8. 2, 8's a little off the grid here. Just play connect the dots. And we have our cube function. Square root function. For the square root function, we're going to change our domain. We're not going to use negative values because you can't take the square root of a negative number without getting imaginary. We want to keep it on the real axis. So we'll choose some starting values that make sense and are easy to take the square root of, such as 0. It's easy to take the square root of 0. We can also easily take the square root of 1. Square root of 1 is 1. Then we can take the square root of 4. Square root of 4 is 2. The next easiest one would be the square root of 9, which is 3. And we could do more if you wanted, but it's going well off the grid, so we'll just stick with these. 0, 0, 1, 1, 4, 2, and so on. Goes off the grid, so we'll just stop there. And there's our square root function. Cube root function. The cube root does not have restrictions, so we can, again, choose some values that are easy to take the square root of. 0 we can easily take, 1 we can easily take, -1 we can easily take, and then 8 or -8 would be the next easiest. So -8, -2 is sort of off the grid. Somewhere over here, then -1, 1, 0, 0, 1, 1, and then 8, 2 again is off the grid a little bit. And so we play connect the dots. And we have the cubed root function. The reciprocal function, notice we can't have 0 here. Division by 0 is undefined. I'm going to write it here in the chart just to make a mental note of it, but it is undefined. So we're not going to have anything that's crossing the origin. But we can choose other numbers such as -1. Plug in -1, we get -1. Plug in +1, we get +1. And now pick any other value that you want for x. Just keep in mind what's happening. As x gets really, really big, the fraction is going to get smaller. So for example, if you did 10, then this would become 1/10. Or if you did -10, this would be -1/10. And so on. As your x values get bigger, the fraction is getting smaller because the denominator x is actually getting bigger. So we have these points that we know are there. Excuse me. -1, -1, and 1, 1 is there. And we're basically going to get a shape like this. It's not going to touch the x or y axis. It'll get really close to the x and y axis, but never actually touch it. This is our reciprocal function. The absolute value function, there's no restrictions on domain, so I'll just stick to the ones we started with initially. -2, -1, 0, 1, and 2. And whenever you plug in your x, those values just become positive. Plot your points. And we get a V shape. There is a sharp corner here. That V shape happens when you have absolute value. It's not a smooth curve like quadratics or other polynomials. There is a distinct V shape with absolute value. Which functions are even? So let's go through and determine which of these are even. We know this one's even. Because it is symmetric about the y-axis. This one is odd because it's symmetric about the origin. Here, odd, symmetric about the origin. This one is neither. It's neither even nor odd. This one, odd, symmetric about the origin. Here we have an even function, symmetric about the y-axis. And this one is odd, symmetric about the origin. See, what is the domain? So we got that one, we got that one. What's the domain of the square root function? Domain of the square root function. So domain, remember domain is your x values. So we're looking for where the x values start. They start at 0, and then they go on forever. So the domain of the square root, 0 to positive infinity, including the 0. What is the range of the absolute value? Range of absolute value. Remember, range is looking at the y values. So where do the y values start? The y values start at 0, including 0, and then go on to infinity. So the range 0 to infinity, including the 0. What are the local min of the function x squared, and where does it occur? All right, so the local min is 0 here, the origin. The x value, or excuse me, the y value is the min. Where does it occur? At 0. X equals 0. So remember, the minimum or the maximum, whatever you're talking about, is the y value. Where it occurs is the x value. Next, we look at piecewise defined functions. These look a little ugly, but they're really not that bad. They're just different functions on different equations on different domains. So it's still one function, we just have two or more equations, and we determine which equation we're looking at by the given domain. So for example, let's practice function notation. F of -3. F of -3, we have to determine which of these equations we're going to use. And we're going to determine that by where our x value is in the domain. So x is -3. That means we're going to be using this equation because -3 is in this restriction. -3 is less than 4. So let's use this equation when we evaluate f of -3. So we're just going to simply replace the x's with -3. And we get -3 over -1, which is 3. Next, f of 4. We have to see where the 4 is to determine which equation we're going to use. Notice there's a 4 in both of these, but only one of them has equality on the 4. That's the first one. So we're going to use x squared plus 1 to evaluate the 4. So plug in the 4, square it, and add the 1. We get 17. And then f of 6. First of all, we have to figure out which equation we're going to use. Figure out where the 6 is, which domain restriction includes the 6. That would be the first one. 6 is up here. It's bigger than 4. So we're going to take the 6 and square it and add 1 to give us 37. Next, let's graph piecewise functions. I like to go back to point plotting when we do these and just take them separately, but we're going to put them on the same graph. So for example, let's look at x plus 1 and graph it. So we'll get some point plotting values. X can be whatever we want it to be as long as it's within this restriction. So I recommend you start with what's given. Start with 1. When we plug in 1, we get 1 plus 1, which is 2. And then we need to pick another x value. Looking at the restriction, we can be 1 or bigger than 1. So let's choose something that's bigger than 1, for example, 2. Plug in 2 and we get a 3. And now let's plot this. 1, 2. You have to ask yourself, 1, 2, is that an open circle or a closed circle? We know it's going to be closed because we have equality here. So 1, 2 is a closed circle. That point, that end point, is part of the graph because we have equality. Next, 2, 3. 2, 3 is automatically going to be closed because we need another point to determine where the slope is. So 2, 3 helps us find the slope, and from there we just play connect the dots. The only one you're ever going to question whether it's open or closed is the end point. So let's do the same thing with the next one. Let's look at x squared and do some point plotting. So we have to determine where to start our domain, which x value do we start with. Start with what they give you. Even though we don't have equality on the 1, still start on the 1. Plug in 1, 1 squared is 1. Then we need something else. We need another value for x. Anything less than 1. Look at your restriction. It has to be less than 1, so let's choose maybe 0. 0 squared is 0. And since this is a quadratic, let's do a third point 2's probably not going to do it for us. 2 was plenty over here because this was a linear equation, but since this is quadratic, we need an extra point. So again, anything less than 1, say -1, and then -1 squared is +1. So your first point we need to ask, is it open or closed? 1, 1 is going to be going to be an open point because we have a strict inequality here. So 1, 1 is an open circle. The only one you're ever going to question is those endpoints. The others, we only get to know what the shape looks like. So 0, 0 is closed, -1, 1 is closed. We only need those to know where to play connect the dots at. And this is our piecewise function. Next, let's look at this one. Again, we'll graph them separately. Absolute value of x is happening everywhere except for 0. So if you remember the function for the absolute value, it'll help you. But if you don't, that's okay. We can plot some points like earlier. So -1, 0, 1. If you plug in -1, we get 1. If you plug in 0, we get 0. If you plug in 1, you get 1. But remember, this one is actually undefined at 0, or not equal to. So we're going to leave an open circle there. But everything else looks like the absolute value function, that V shape from earlier. We have the absolute value function, except for at 0, it's not going to be the absolute value when we're at 0. Open circle. And then the next part, at 0, when x is 0, we get a 5 and nothing else. There's no equation, there's just this constant 5. So it's just a point.